guys. Before we start today's class, I hope I'm audible. Am I audible? Am I audible?
Yes, ma'am.
Yeah.
Yes, ma'am.
So before we go ahead, I'll just summarize what we have seen in the last class. We talked about flux, the concept of flux, and we started our discussion using fluid flowing through a pipe. Okay, first we assume that the field line representing the flow is the velocity vector. And then we talked about what is flux. Flux is volume flow rate we have seen. And in terms of an equation, flux is V dot A, where V is the velocity vector and A is the area vector. And this V dot A holds if V is uniform over an entire surface. Like for example, here I've shown you a rectangular surface having some area A, and the normal to that surface is your area vector direction. Now, if the velocity vector is uniform, then you can use this formula phi equal to V dot A. On the other hand, if look at this picture here on the right hand side. Okay, on the right hand side we have another picture. So here the surface is not a plane surface, it's a curved surface, and the velocity field is also not uniform, the lines are diverging. So in that condition, how do you find out what is phi? In this case, phi will be integral V dot dA. Integral V dot dA. And what is the dA vector? dA vector is a small area vector of magnitude dA, and the direction is the outward normal drawn at that point. So you have to just do V dot dA, taking into account this angle here. Similarly, for each of these things you do, for every point on the surface, and do a summation or an integration, so you get integral V dot dA. And please remember, this is used whenever the V vector is non-uniform or the surface is not a plane surface. The next thing we have seen is that flux can be negative, flux can be positive. Flux is positive if the angle made by the A vector and the E vector and the dA vector is theta, and theta is lying between 0 and 90. You know that cos theta is positive whenever theta is between 0 and 90. And this flux will be negative if your E vector and your A vector are making an angle theta which is greater than 90. Because after all, you know that cos theta is negative when theta becomes greater than 90. Okay? Or you also see that in the first picture, the field is emerging out of the surface. If this is my surface, the field is emerging out of the surface. Whenever the field is emerging out of the surface, flux will be positive. In the second picture, you see, field is actually entering the surface. Field is entering this surface. And you can see that flux will be negative. Okay. After we were done with this, we went to closed surfaces. We talked about situations where you have a closed surface and you're talking about flux for a closed surface. So for a closed surface, flux will be positive if this closed surface encloses a source. Okay, because from the source you're going to have flow outward. Flow outward. Therefore, flux will be positive. On the other hand, if what you have inside the surface is a sink, then lines will be going towards the sink. Water will be flowing towards the sink. In that case, field lines are entering. So therefore, flux will be negative. Now let us generalize and say, what will be flux if there is no sink or source? What will be flux if there are no sinks or source enclosed? What do you think will be the answer?
Zero.
Zero. It will be zero. And also we've seen in the first class that, sorry, I'm writing E here, that's by force of habit. You should write everywhere. I'm writing E. Okay, so let me just correct all this. This should also have the B vector. V vector, that's my dA vector. Similarly here also, I'm talking about field line going out. So that's my V vector. Okay. So flux will be zero if there are no source or sink. And in the first class, I also said something. Flux can be pictorially represented by the number of field lines cutting through a surface. Number of field lines cutting through a surface. Now, if I'm going to take a closed surface where there are no source or sink, then what happens is the number of field lines which will be going through it will be like this. Three lines are entering, three lines are emerging. Like in this picture, three lines are entering, three lines are emerging. So therefore the flux will be zero. So you can just look at the picture itself and say whether the net flux will be positive or negative. If more number of lines are coming out than entering, then it is positive flux. Okay? Now, once we are done with this, let us move to flux for an electric field. Flux for an electric field. Wherever V vector was there, now replace with electric field. That's all. Okay. Flux for an electric field E through a surface is defined as phi E. This E subscript stands for electric field. Phi E equal to E dot A. And remember, this is if your surface is a plane surface and your field is uniform. Field is uniform, meaning field is having the same value at all points on the surface. The field is having the same value at all points on this surface. Then you say that flux is equal to E dot A. And let us look at the unit. You know that electric field is Newton per Coulomb and area is meter square. Therefore, the unit will be Newton meter square per Coulomb. Okay. And again, what we said there holds good here. Electric flux is proportional to the number of electric field lines cutting through an area perpendicular to the field. If I'm talking about fields like this, and if I'm holding an area perpendicular, so the number of lines cutting through this perpendicular area represents the value of the flux. Okay. Now again, taking this idea forward, let us go to non-uniform electric field, an arbitrarily shaped closed surface. In that case, what happens is, like what you have done in the previous case, flux will be integral for the closed surface E dot dA. There we wrote V dot dA, here it is E dot dA. Now, what is this E? What is this dA? Let us say. Let us say this is my arbitrary surface, closed surface, and I am talking about electric field. Let's say I'm talking about some electric field which is like this. Okay? Then I can see that the electric field is non-uniform. Electric field is non-uniform, I can see here. Okay, and how do you integrate this E dot dA? So what you do is, at every point, you have to consider an area vector dA, and the direction of the area vector will be an outward normal. An outward normal. This is my E vector at this point. Then look at the angle theta. So integral E dot dA, you will do for this area. Like this you do for the entire surface, then what you get is integral E dot dA. Okay? And how do you choose your dA? dA should be so small. dA should be so small that for that area, E should be uniform. For that area, E should be uniform. Okay? And it should be so small that you can almost consider it as a plane surface. And then the direction is the outward normal. Okay, and what is E vector value? E vector value is, depending on which is the point you're taking, whatever is the E value there, so that is your E vector value. So this way you do an integration, what you get is called the electric flux. Now going ahead, what you've done there holds good here also. So here is a picture of electric field lines. They are not uniform. This is an arbitrary closed surface. And I told you at every point, you can take a small area, okay, and then draw the outward normal and look at the electric field at that point, and then calculate E dot dA. Like that you do for the entire surface. That is integration. Okay, and once more you see here, flux is negative. Flux is negative for field lines entering a surface. This is what I told you. flux is negative if field lines are entering a surface. Look at this picture here. For this surface, for example, for this first surface given here, you can see that the electric field line is entering. Field line is entering into the surface. This is your electric field vector. And the area vector is a normal that you draw at this point. So that's your area vector. Okay, and you can look at the angle between them. The angle between them will be greater than 90 degrees. Therefore, for this area, flux is negative. Now look at this surface. So here you see field lines are like this. Area vector is like this. Okay, you can see that field and area are making an angle 90 degrees with respect to each other. So this is the picture. Cos 90 is 0. So you know that field line is not cutting through that area. Therefore, flux is 0. Whereas in this case, flux is negative because theta is greater than 90. Now let us come here to the part C. C, you see, electric field is cutting out of the surface there, and you can see that your area vector is an outward normal. If I draw E and area vector, you find that the angle is less than 90. Therefore, flux here is positive. Flux is positive. Here, flux is negative. Where it is not cutting, flux is 0. Okay, so you summarize it as for any given surface also, you can talk about different regions having positive and negative value. Flux is negative if field lines are coming into the surface, entering. Theta will be greater than 90. Flux will be 0 if field line is not cutting through a surface. There theta is 90 and flux is 0. Flux will be positive if the field lines are emerging from a surface. The emerging means going out of a surface. There theta will be less than 90. Okay. Now, whether this net flux for the entire surface is going to be positive or negative depends on how many lines are entering and how many are going out. If the number of lines entering is equal to the number of lines going out, then flux is 0. If the number of lines entering is larger than the number going out, flux will be negative. If the number of lines entering is less, what is going out is more, then it is positive. Okay? Okay, so now here is a picture. We have to try out this problem. You have a uniform electric field represented by uniformly spaced parallel lines. That means at every point, electric field is having the same value. Now what you have to do is take a cylindrical pipe. Take a cylindrical pipe, put it in the electric field so that the axis of the pipe, axis of the cylinder, and it's a closed cylinder, okay? The axis of the closed cylinder is parallel to the electric field. It is parallel to the electric field. And now you have to find out what will be the flux. Without doing maths, can you tell me what the flux will be? Without doing any maths. Just by looking at the picture, can you tell me what the flux will be?
0, ma'am.
0. Why 0?
Because number of lines entering are equal to the number of lines leaving.
Yeah, you can see 1, 2, 3. 3 lines are entering or cutting and entering. 3 lines are cutting and coming out. And for the curved surface, this curved surface, you're finding that no line is actually cutting into. There's nothing cutting. Therefore, the flux for the curved surface is 0. Okay? And the number entering is equal to the number emerging. Therefore, flux is 0. But we can also mathematically do that. So how do you do that? Treat this as 3 surfaces. Surface A, surface B, and surface C. Treat it as 3 surfaces. Individually do the integration for the 3 and then add them up. Okay, therefore you have for surface A, E dot dA, surface B, E dot dA, surface C, E dot dA. So first we'll look at surface A. Let us look at surface A. Surface A means I'm talking about this circle. I'm talking about this circle. And if you look at this circle, at every point on this circular surface, the electric field is normal and has the same value. Normal and has the same value. And let us look at the area vector. Area vector is outward. Outward. Or you're finding that for the surface A, you're getting the area vector in this direction and you're getting the electric field direction as this. So what is theta? What is theta? Angle between E and A vector 180 degrees. You know cos of 180 is minus 1. Minus 1. Therefore, here what happens is integral E dot dA. Integral E dot dA for surface A will be simply minus integral E dA. I am removing my vector sign here. You must be noticing. E dot dA is E dA cos theta, cos 180. So minus 1. Okay. Now, E is the same for every point on the surface. So what I can do is I can take E is a constant. I take it out along with the minus sign and then do integral dA. What will be integral dA for this surface? It will be simply the area of this circle. So the area of that circular surface, let us say it is A. Therefore, it will be minus EA. Okay. Now, similarly for surface B, let us see. Sorry, for surface C, let us see. For surface C on a similar ground, you can see that E vector is coming out of the surface, but your area vector is always an outward normal. So you find that theta equal to 0 degrees, or flux will be equal to plus EA. Whereas here flux will be equal to minus EA. Then for the surface B, flux will be equal to 0. 0 because no line is cutting through it. Electric field and area vector are making an angle 90 degrees. Now let us look at the sum of all this. What will be the sum of all this? Minus EA plus 0 will be 0. Okay, so you can also see that there are no sources inside. No source or sink is there inside. I'm saying no source or sink because if there was a source or sink inside, number of lines entering would not be the same as the number of lines going out. Okay, now I've been using word source and sink. I told you what is source and sink for velocity flow, but here I've not told you what is source and sink. Let us see what source and sink mean. So here, let us look at an imaginary closed surface. Please remember this is a closed surface. It is a three-dimensional surface. And I have a negative charge. I have a positive charge at the center. I have a positive point charge at the center. What are the sources for electric field? Anyone can tell me? We have been talking about source. This word source we didn't start now. We have been talking since last chapter. What are the sources for electric field?
Charged particles.
Charge is a source for electric field. So here let us say that I have a positive charge at the center of this three-dimensional closed figure. You know how for a point charge how the electric field will look. The electric field will be radially out in all the along 360 along this entire surface. Electric field will be radially coming out. Okay. Now you can see that therefore the field lines are cutting out or emerging out. Field lines are emerging out. Now when you come here, you are seeing that field line is emerging. Here it is entering. Here it is emerging. So on the whole, what will it be on the whole? It's the same line. Entering, emerging, entering, emerging. So which is strong? Emerging or entering?
Emerging.
Emerging. So this is also emerging. So how many lines are emerging? 1, 2, 3, 4, 5, 6. Everything is emerging. Everything is emerging. So what is the net flux? Flux will be positive or negative?
Positive.
Positive. Therefore, flux will be positive. Flux will be positive when field lines emerge from a closed surface, because I already told you, theta will be like, for example, here if I'm going to draw my area vector, okay, I find that my area and my E vector are going to make an angle theta less than 90. Or you can also conclude that for a closed surface, if what you have inside the closed surface is a net positive charge, then the flux will be positive. Flux is positive when the net charge inside is positive. Similarly, let us think of what will happen if I have some random shape, three-dimensional object, and I have a negative charge. If I have a negative charge, how will my field lines look? A point negative charge? Radially?
Inward.
Inward. Radially inward. So everywhere on my Gaussian surface, I find that the field line is entering. Therefore, flux has to be negative. Flux has to be negative. I find that my E vector and my A vector and my, let me say, BA vector and my E vector are making an angle greater than 90. Flux will be negative for every point here. Therefore, the net flux also will be negative. Okay. What if there are no charges inside? I have my surface. There is no source. So I call this as sink. My negative charge becomes a sink because it is pulling the electric field towards it. And positive charge is called a source. Okay. Now, what if my surface doesn't have charge or sink? And let me say my field lines are all like this. Then I see that number of lines entering is the same as the number of lines emerging, which means there is an electric field, there is a source, but the source is not inside the surface. My source is not inside the surface. Source may be somewhere outside. Okay? Only the electric field lines are actually entering and going out of this surface. And in this case, flux will be equal to 0. You must have noticed that I'm gradually leaving that subscript E. I'm leaving the subscript E because now we know we are talking of electric field lines only. Or we conclude that electric flux through a closed surface enclosing a net negative charge is negative. Electric flux through a closed surface including zero charge is 0. Okay, let me just ask you a question. Let's say I have a surface and within this I'm having positive and negative charge. This is 4 nanocoulomb and here I have minus 2 nanocoulomb. What will be flux for this surface? Positive or negative?
Positive.
Positive, because the net positive is more than negative. Similarly, I can have a situation where I have a dipole. Let's say I have a dipole inside a surface. What's a dipole? A positive and a plus q and a minus q separated by a distance. What will be the net flux through this? What will be the net flux if I have a dipole inside? I think people who are answering are also, I expect them to answer all the time. Why don't somebody else just jump into the fray and answer? Guys, why don't you talk? There's a plus q and a minus q. That is a dipole enclosed by a surface.
Ma'am, is it 0?
What will be the net flux? 0. Because what is the net charge inside? You have to look at this. I've been underlining net everywhere. Net. So the net charge is positive, flux is positive. The net charge is negative, flux is negative. The net charge is 0, flux is 0. Field may be there, like in that picture that I've shown you. This picture. Field is there, but then flux is 0. Because there is equal positive flux and negative flux. So sum is 0. Here is another pictorial representation. Remember, it's only a pictorial representation. Don't jump and ask me, ma'am, you taught us that electric field lines should not cut each other, but then in that drawing it is cutting. This is just a pictorial representation. Okay, so don't ask me that question. So first of all, I want you to recall something. Number of field lines originating from or terminating on a charge is proportional to the magnitude of the charge. Have you seen this somewhere? Number of field lines starting from a charge or ending on a charge is proportional to the magnitude of the charge. Have you seen this somewhere?
Yes, ma'am.
Yes. Last chapter we have seen. If I have a 4 nanocoulomb charge and a 2 nanocoulomb charge, number of lines from the 4 should be double of what you are drawing on from 2. Okay, this you know. Next, I want you to recall something. Field lines start on a positive charge and terminate on a negative charge. This also we studied in the last chapter. Keeping both these pictures in mind, let us just look at this picture here. I have 1, 2, 3, 4, 5, 6. 6 lines are coming out of my surface. Here, 1, 2, 3, 4, 5, 6. 6 lines are going in. So what can you conclude about the magnitude of this positive and negative charge?
Both have the same magnitude.
They have the same magnitude. Now let's go to the next picture. The next picture, I have both of them inside. And I can see the number of field lines emerging is equal to the number of field lines entering. This is just a pictorial representation, okay? Basically, we're trying to tell that you can just look at the drawing, you can look at the field lines itself, field line distribution around the surface itself, and understand a great deal about what is a flux. Then, another very interesting thing that you should understand is that the net flux through a surface enclosing a charge does not depend on the size or the shape of the surface. It only depends on the net charge enclosed. It does not depend on the shape or the size of the surface, closed surface. It only depends on what is the charge inside. I'll give you an example. Let's say I have a positive charge here, and I have a surface 1, which is a perfect sphere. Okay, this is my surface 1. Then I have another surface. Let's say it is like this. I'll call it surface 2. Okay, now if I draw the field lines for these, field lines for this, okay, let's say I've drawn 6 lines. There is no 6 lines is not a golden rule. Just like that, I drew 6. That's all. Okay, now you see how many lines are emerging out of surface 1? How many lines are emerging out of surface 1 and 2?
6.
6. Therefore, the flux is the same for both surface 1 and surface 2. Now I'll draw one more surface. Surface 3. What is the flux through this? Is it the same as S1 and S2?
Yes, ma'am.
Yes, because you know that field lines never stop in mid-air. Okay, it's the same number of field lines which are entering and emerging. Right? For example, here you see the same line emerged, entered, emerged, therefore emerged. And then you see the number of lines emerging, it is 6. So you conclude that the net flux does not depend on the shape or size of the surface enclosing, it just depends on the magnitude of the charge inside. Okay, because after all, you know that number of field lines and starting or ending on a charge depends on the magnitude of the charge. Okay, now we come to a very important discussion. So now we have found that flux is related to net charge enclosed. Okay, and you're going to see that there is a relationship, a mathematical relationship between this flux and the net charge enclosed. And this mathematical relationship will hold good for any shape or size of the closed surface. But you can put this relationship to use. You can put this relationship to use and evaluate the electric field at a point only if the geometry of the charge distribution, the surface, and the field match. Relationship between phi and charge is always valid, but you can put this to use and evaluate the electric field at some point if the geometry of the charge distribution. It's a line, it's a sphere, it's a shell, okay? That geometry, and therefore the geometry of the electric field. These two should match with the geometry of the surface you are considering. If these three things are matching, then you can use this relationship and evaluate the electric field at some point. Okay, so next we are going to see what is this mathematical relationship between flux and charge enclosed. So that's going to be called your Gauss law. So what does Gauss law say? Gauss law says that the net electric flux through a closed surface, let's say we have a closed surface like this, and it is enclosing a number of charges Q1, Q2, Q3, etc. till Qn. Okay, then the net flux through this closed three-dimensional surface will be integral E dot dA will be equal to Q by epsilon naught. What is this Q? Q is the net charge. Q is the net charge enclosed. Or Q is going to be equal to Q1 plus Q2. You go on till you reach Qn. Of course, you're going to add, taking into account the sign. Okay, so Q is the net charge. That's why we kept using the word net charge enclosed, net charge enclosed. There is a relationship between flux and the net charge enclosed. Okay, now this relationship between these two is called your Gauss law. That's called Gauss law. And this surface, we kept talking about the closed surface, closed surface. This closed surface is called your Gaussian surface. And remember, Gaussian surface may be a real surface, it may be an imaginary surface, or half of it can be real, half of it can be imaginary. Okay? But this equation always holds good. So now look at this interesting thing. You look at this equation for Gauss law, flux is equal to Q by epsilon naught. You are seeing that in this part of this equation, okay, the geometry of the surface is not at all figuring. The geometry, the shape and size of the surface is not figuring. Directly by knowing what is the net charge enclosed, you can find out the flux. Now to understand more about flux, we will take an electric dipole. Let's consider an electric dipole. You can see there is a plus charge, there is a minus charge of equal magnitude, separated by a distance. And in the previous chapter, we have seen how the field lines will look for a dipole. Field lines will be starting from a positive charge, and some of those lines will end up on the negative charge. But if you see the number of lines you're drawing for a positive charge or a negative charge, you will find that they are equal because they have the same magnitude. Do you remember this? Electric field line distribution? You can remember it only if you have studied. Okay, so now what we'll do is, this is a three-dimensional thing, okay? Don't imagine a positive charge, negative charge. So when you're drawing field line, don't imagine on a surface like this. It's not a flat page. It's actually drawing like this, like this, like this in three-dimensional space. Okay, now what we'll do is, let us consider a surface 1 enclosing only the positive charge. Enclosing only the positive charge. Surface 1 enclosing only the positive charge. What will be the flux according to Gauss law? What will be the flux according to Gauss law? If for some reason I find that you people don't interact with me, are you scared? Or is it that it is not at all interesting? Or is it that you have just logged in and gone off to do your personal work?
No, ma'am.
So then why don't you interact? Why don't you talk? In fact, I want you people talking and me saying shut up. It should be like that. Talking means not your personal things at home. or you talking to your puppy at home and all that, not that. But you should be interacting. Please talk, otherwise, So Satya Nitin has left the meeting. Maybe the fellow thought I'm going to ask him something. Okay, so now for the surface 1, can you tell me what will be the flux? What is the net charge enclosed?
Q.
Q plus Q. Therefore, plus Q by epsilon naught. And if I write the equation, it will be for the closed surface S1 E dot dA. Now, similarly, for the second one, you see, second surface, what will be the flux? Flux will be minus Q by epsilon naught because the charge I have is minus Q. And now look at the number of lines for Q, for plus Q and minus Q. For plus Q, you see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm finding that some 10 lines, 10 or 11 lines are coming. How many lines are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 lines are coming out. If you see for surface 2, 12 lines are entering. Now, for surface 3, what will be the flux?
Zero.
Because there is no charge. For surface 4, what will be the flux? Surface 4 is enclosing both the positive charge and the negative charge. Therefore, the flux will be
0.
0. Even look at the picture, you're seeing that the number of lines entering is equal to the number of lines emerging out. Okay? So you should understand both these concepts. The concept of flux mathematically and also pictorially in terms of field lines cutting. Okay, next what we'll do is the general rules when you are considering a Gaussian surface. I told you Gaussian surface can be imaginary surface. So depending on your necessity, you have to choose a Gaussian surface. Okay, so how do you choose a Gaussian surface? The first golden rule is choose a Gaussian surface shape so that there is a symmetry between the field and the surface. Like for example, if I have a positive point charge, what is the field symmetry for this? What is the geometric symmetry for the field for a point charge? I've used a word. Do you remember? Some symmetry I have used. What is that symmetry? Anyone remembers?
Spherical symmetry.
Spherical symmetry. I've used the word spherical symmetry. So the field lines are going to be make a sphere in all the direction, a sphere. So it will come out like this. There is a spherical symmetry. So what you have to now do is choose your Gaussian surface also as a sphere. Your Gaussian surface also should have the same shape. It should be a Gaussian surface which is spherical. Next, Gaussian surface can be real or imaginary, or it can be a mix of the two. Okay, that's something you have to remember. Next, the size and shape of the Gaussian surface surrounding a charge does not determine the line value, integral value. Because after all, flux is equal to integral E dot dA equal to Q net by epsilon naught does not depend on the geometry. It does not depend on the shape or size. So you have to remember that the integral value is not going to depend on the shape or size, but choose it in such a way that there is a symmetry. Next, if electric field is 0 at all points on a Gaussian surface, let's say I draw a Gaussian surface, I don't have any charge anywhere inside or outside. I don't have any charge anywhere inside or outside. If there is no charge at all, will there be a field in that region? If there is no charge anywhere near that, will there be a field there?
No.
No. Okay, so that means at every point on this, electric field is going to be 0. So if I do integral E dot dA, it has to be 0. Okay, the next thing is, if the electric field is parallel to a Gaussian surface, if the electric field is parallel to a Gaussian surface, what do I mean by that? If the electric field is parallel to a Gaussian surface, E dot dA is 0 because theta is 90 degrees. Because theta is 90 degrees. Like you remember cylinder, that cylinder and surface B. So what did we have here? We had our electric field. Electric field was parallel to the surface. I'm not saying area vector. Please note down what I'm saying. Electric field is parallel to the surface. If it's parallel to the surface, it is not going to cut the surface. Therefore, this angle will be 90 degrees. Your area vector will be forming an angle 90 degrees with E. So, if the electric field is parallel to any surface, flux is 0. So, let us see the continuation of this. If electric field is uniform over a Gaussian surface and is outward like here, electric field is uniform at all points, okay, and it is perpendicular to the surface. This is my surface and it is perpendicular. Then I can say that my area vector and my E vector are parallel to each other, and electric field is having the same value at every point on this. Therefore, integral E dot dA will become EA cos theta, and it just becomes E into E. Okay, next. Another very important thing you have to remember is that, let us say I have a charge Q prime here. I have my Gaussian surface here. I have a charge Q here. Okay? Now, very important thing that you should remember is that at any point on the Gaussian surface, electric field will be because of both of them. Electric field will be because of both the charges inside and outside. Okay? But the flux will be only because of which charge?
Enclosed in the cell.
Enclosed charge. It will not be because of Q prime. Even though you have a charge Q prime outside and it is contributing to electric field everywhere on the surface, still when you do an integration, this fellow's contribution will become 0 to flux. Q prime's contribution to flux will become 0 because the number of lines entering and emerging will be the same. But Q will contribute. So this is another very important thing that you have to remember. And then finally, to close it, integral E dot dA of flux will be positive if the net charge enclosed is positive, negative if the net charge enclosed is negative, and 0 if the net charge enclosed is 0. So you have to remember all these rules when you are dealing with any problem on Gauss law. So what we will next do is, at the beginning of this chapter, I told you that Gauss law is a more general law. It's a more general law, and it is a law that you are going to use everywhere in your Maxwell's equation. Coulomb's law is just a particular case of Gauss law. Coulomb's law is just a particular case of Gauss law. Like for example, what is a rhombus, or what is a rhombus? School maths, I'm asking. What is a rhombus?
Quadrilateral.
Quadrilateral. Is rhombus quadrilateral? Okay, what is a quadrilateral? Quad means? Quad means what?
A polygon with sides.
Polygon with 4 sides, right. And no restriction on the sizes or the ratio of the sizes of the 4 sides. No restriction on the angle. That is a quadrilateral. Okay, now tell me what's a rhombus? I'll cry now. What is a rhombus? Hey, you have your phones now, look at it. You have forgotten all your mathematics from school. You have something called a calculator with you. You all have this. Okay, just open it. Okay, there is something called Google. Just Google. Okay, Google, type rhombus and ask what is a rhombus. Please, in case you don't know, I will tell you even that. What is a rhombus? Akshara, what is a rhombus? Diagonals are not equal. Hey, don't type here, you talk. Because I have to otherwise, come out of that screen and see what you're typing.
A quadrilateral whose diagonals are perpendicular bisectors and lengths are equal.
Great. So, will you agree that it is a subset of a quadrilateral?
Yes, ma'am.
Right. What is a square?
Quadrilateral with all sides equal and angle between the sides is 90.
90. So, that is a subset of rhombus.
Rhombus.
And rhombus is in turn a subset of quadrilateral. Same logic you apply here. Coulomb's law is simply a special case of Gauss law. Gauss law is something more general. So in 2 minutes, I will show you that Gauss law and Coulomb's law will compare, and we will arrive at Coulomb's law from Gauss law. So use Gauss law and determine the electric field at a point. So what is Coulomb's law? Anyone? Coulomb's law is Coulomb's law. I'm not asking about force. I'm asking about the field equation. Coulomb's law, electric field is F by Q naught, which is equal to 1 by 4 pi epsilon naught Q by R square. Okay, so this is your Coulomb's law. You have to arrive at the electric field expression for a point charge at some distance using Gauss law. Arrive at the same result. So what do? Take your point charge. Let this point charge be positive. Let it be Q. And I am interested in finding out what is the electric field at this point, which is at some distance R. Okay. Now I know that the electric field is having and the charge distribution, electric field, and what is after all a point charge? A point charge is a tiny sphere. Okay, so therefore electric field and charge distribution both are having a spherical symmetry. There is a spherical radial symmetry. Okay, so next what do? I need to now use a Gaussian surface which matches this symmetry. Therefore, my Gaussian surface is going to be a spherical shell. It's going to be a spherical shell with this charge Q at the center. And how do I decide the size of the Gaussian surface? My Gaussian surface is a sphere of radius R. I need the radius to be R because I want to find out what is the electric field at let us say this is a point P. At a point P, distant R from the charge Q, I want to find out the electric field. Therefore, the golden rule is, I have told about so many golden rules. So one of the golden rules is my spherical Gaussian surface should be drawn in such a way that on it will lie my point P. Okay. Next, I have to also now realize that electric field is uniform at every point on the sphere. That's what is spherical symmetry. At every point on the sphere, the electric field is uniform, has the same value. Uniform means, don't say, ma'am, you're not drawing parallel lines. No, what we mean by uniform is, it is having the same value at every point on this sphere. Okay? And additionally, I find that the electric field is perpendicular to the surface at every point. At every point on the Gaussian surface, electric field is making an angle 90 degrees. And if I take a small area dA here, I find that my dA vector and my E vector are parallel to each other. E is parallel to dA vector at every point on the surface. Additionally, E has the same value at every point on this Gaussian surface. So these are the two important things. So now what we'll do is let us apply Gauss law. Flux is equal to integral E dot dA for this surface. Okay. Now I know that in E dot dA is equal to E dA cos 0, which is E dA. Okay. So I write E dA, and then I find that E is a constant for the entire surface. So I can pull it out of the integral. I take out my E, then I have my integral dA. What is my integral dA? And this is a sphere. This is a sphere. Therefore, integral dA will be E into A, where A is the surface area of the shell. Surface area of the shell. You know what is the area of a spherical shell? It is 4 pi r square. And what about the right hand side of this phi E? Phi E is integral E dot dA, but Gauss law says that it is going to be net charge by epsilon naught. Net charge is Q by epsilon naught. So now I'm interested in finding out the electric field at that point. Therefore, E you keep on one side of the equation. Get 4 pi r square to the other side of the equation. So I get Q by 4 pi epsilon naught r square. 1 by 4 pi epsilon naught Q by r square. Now what is this? What is this that we have got?
Electric field at a
point charge that we got from Coulomb's law. So now you know that Coulomb's law is just a special case of Gauss law. Gauss law is something that can be applied to even charges which are not point charges. But Coulomb's law can be applied only to point charge. In that sense, Coulomb's law is just a special case of Gauss law. So in the next class, what we'll do is we will apply Gauss law to charges which are not point charges. We will apply them to extended continuous charges. Any doubts on what we have studied today? If there are no doubts, we'll wind up now. Okay. Good day then.